Hello. This lecture will cover pages 112 through 115 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Additional Analysis Techniques, Chapter 5E, the Maximum Power Transfer Theorem. We're going to start on page 112, and we're going to talk about something that's extremely important in engineering called the Maximum Power Transfer Theorem. The Maximum Power Transfer Theorem states that a load will receive maximum power from a linear bilateral network when its total resistance is exactly equal to the Thevenin resistance of the network as seen by the load. So Thevenin's theorem plays heavily in this maximum power transfer concept. If you take a look, this is a Thevenin equivalent circuit. We've worked a number of those, at least we will in the last lecture. There's a final lecture to go, and we'll work a number of problems in the final lecture. But here we're going to look at this circuit as a Thevenin's theorem, as a Thevenin equivalent. Here's your Thevenin voltage, and here's your Thevenin resistance. What Thevenin's theorem, what the maximum power transfer theorem tells you is maximum power will be delivered to this load resistor RL whenever RL is exactly equal to the value of the Thevenin resistance. That's a pretty powerful statement. We're going to prove it in a minute. But for now, I want you to look at this circuit and use some simple analytical techniques to come up with these two equations down here, which you'll use on the exams and quizzes. Since the load RL is in a series circuit, this is a series circuit, this Thevenin equivalent. Since the power in the load is equal to the current squared times the resistance, this power out here in this load resistor is simply equal to the current flowing through it squared times the resistance. We can make a substitution for the current. We know the current in this circuit is equal to the total voltage E Thevenin divided by the sum of these two resistances, which is R Thevenin plus RL. So what we have here is the current I in this circuit. We're going to square it, and we're going to take it times RL, and that gives you the power in that load resistor in terms of watts. Now, that equation is useful to determine what the power is dissipated in the form of heat in this resistor, but under a maximum power transfer condition, this RL is equal to R Thevenin. So we can replace RL here and RL here with R Thevenin. And if we do that, since RL is equal to R Thevenin, for maximum power transfer, we can change this equation to this one. Instead of simply being the power in the load, we can say the power in the load maximum. The maximum power in that load resistor is going to be equal to E Thevenin squared divided by 4 times R Thevenin in watts. Look at that equation. That equation is telling you that you can determine the maximum amount of power that can be delivered to a load out here, independent of what that resistance value is. You don't need to know what that is, because it has to match that to get a maximum power transfer. All you need is the Thevenin voltage and the Thevenin resistance. It all comes from this equation by setting RL equal to R Thevenin. So if I ever ask you what is the maximum amount of power you can get to a load, find the Thevenin equivalent circuit and use E Thevenin here and R Thevenin there. E Thevenin squared divided by 4 R Thevenin. And that's your answer. That will be your answer. For the circuit on the previous page, what I want to do here is, we didn't prove this. I just made a comment that maximum power will be delivered to that load resistor whenever that load resistor equals the Thevenin equivalent resistance. But for the circuit on that I just looked at here on the previous page, we're going to plot the power in the load versus the load resistance. If we let E Thevenin equal 10 volts and R Thevenin equal 5 ohms, and we're going to vary RL from 0 right through infinity ohms. So basically it's pretty easy concept here. on this paper, you can write 10 volts here because that's what we're going to make E Thevenin. 5 ohms here. Put a 5 ohms up there for R Thevenin. And we're going to vary this resistor. That's why I'm showing it as a variable resistor here. We're going to start out by making it 0. And we're going to plot power in the load versus RL. Versus that value right there. And we start at 0. When that resistance is 0 ohms, what's the power going to be developed there? Well, power is I squared R. Isn't it? Power here is I squared R. And if R is 0, the power has to be 0. There's no resistance. So that's a point right here. With RL being 0, the power's 0. Let RL go to infinity and make this an open circuit. If that's an open circuit, that's an infinite resistance. No current can flow in that circuit. So if no current can flow in the circuit, you're squaring 0 times RL to get the power. You're going to be at 0 watts with infinite resistance for RL. This is asymptotic to this line right here, so it's asymptotic to that line. But you have 0 at this point power, way out here in infinity. You have 0 here. What happens in between? Well, what's going to happen in between is it's going to increase to a certain peak value, and then it's going to come off. Exponentially, it's going to come off and decay, the power. That point at which it peaks on the maximum power happens to be when RL is exactly equal to R Thevenin. But I didn't prove anything. I'm just basically telling you what I told you back here. But we know that the power in the load is equal to this. This is what the general power in the load is equal to. So since the power in the load is equal to, now I'm going to do time variant here, the voltage with respect to time, Thevenin, divided by R Thevenin plus RL. That's the current. You take the current squared times RL. That's the power in the load. It's basically this equation down here, using time-sensitive values for E Thevenin, for V Thevenin. Well, all we're going to do is take the derivative of this with respect to RL. Now, you're not taking the derivative with respect to time like you did in most of your calculus classes. You're taking the derivative of this, your derivative of the power in the load with respect to RL, with respect to this. Okay? So, and then we're going to set it equal to 0. Because where's the derivative of this equal to 0? Well, we don't know where it is here. Well, we're going to find out. So, how do you take the derivative of this with respect to RL? Well, I think it's referred to as the quotient rule when you worked it out. It's been a number of times, but I think it's the bottom here, the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared, if I recall it correctly. But that's what that is right there, if you take your time. It's equal to 0, which yields RL equal R Thevenin. That's the proof that maximum power occurs whenever that load resistance matches the Thevenin equivalent resistance. That's why it's so important to find the Thevenin equivalent resistances. And you're going to have a number of problems to work out, but I mean these are fairly straightforward to work out, but here's some learning assessments here. Given this circuit, find RL right here for maximum power transfer. Okay. And then find that maximum power in watts. Well, here's the answers. Down here's the same thing. Find RL here for maximum power transfer. Then find that power of watts that can be transferred. You're just working both of these equations out to get these answers, and you're just using these equations right here. Matter of fact, you're using that equation right there. This concept here, and that equation right there. I want to mention something here, a couple more things yet. On page 113, 114, maximum power does not mean maximum voltage efficiency. How can it be? I mean, I can show you here it's only 50% efficient if you work through power out over power in, but gee, you can see that from this. I don't care what voltage that is here, the Thevenin voltage. If that resistance equals that one, the voltage divider rule tells you get half the voltage across that. That's 50% voltage efficient. Maximum power transfer does not mean we have reached maximum efficiency. There it is again. There's a Thevenin voltage, there's a Thevenin resistance, there's a load resistance matching the Thevenin. That's maximum power. You'll get a maximum power delivered to that resistor, but it'll only be 50% voltage efficient. If you want voltage efficiency, make this resistor here much, much greater than the Thevenin. You don't get maximum power transfer, but you'll get a maximum efficiency. You get 95% efficiency. If that's 100 ohms and that's 5 ohms, figure it out here. I did it here. Now, I want you to think of something here. In some cases, you want maximum power. In some cases, you could care less about maximum power. You want maximum efficiency. So this is food for thought. Let's say you're designing a stereo amplifier. You work for the Bose Corporation, and how are you going to get maximum power to the speakers? You want maximum power to those speakers? You want maximum voltage efficiency to those speakers? What are you trying to do to get that sound out there? You want maximum voltage? You want maximum power? You're going to want maximum power efficiency. You match those speakers to the output resistance of those power transistors or those power circuits. Essentially, that output impedance or that output resistance is, in effect, Thevenin's resistance or Thevenin's impedance. But what if you're the power company and you're generating power? Think about that. You want to get maximum power transferred from the power company. You want to get maximum voltage efficiency transferred. There's no way in heck these power companies could work on maximum power transfer. Would never happen. They'd be wasting half their power in the lines. So what they do is they run really, really high voltages. Very high voltages. With low currents. And they try to reach maximum voltage efficiency. Another way of looking at that, and it relates to it, is if you want a certain amount of power. Well, there's two ways you can get power. Look at this. This is fun to look at. There's two ways you can come up with power. You can come up with power with I squared R, or you can come up with power is V times I. That's two ways of getting power. Thinking in terms of those equations here, you're the power company back here, and you're trying to get power out here to a house. And there's resistance all along here. Well, the power you're going to lose right there in that distributed resistance, which is much less than the load resistance here, the house resistance, if you will, if you're looking at a purely resistive house resistance. You want to keep this power, this current very, very low. If you keep the current real low and the voltage real high, you can get the same amount of power. You can increase voltage and lower current. And if you increase voltage just as much as you're lowering the current, you can keep the power the same. So what we do is they run real high voltages with real low currents. Why? Because low currents, you have less power loss in the line. It's I squared R. What if they ran real high currents and real low voltages? What if they ran 120 volts the whole way to the house? They don't do that. If they did, these currents are going to be real high. And the current here is going to be real high, and you're squaring it times resistance. You're going to get a tremendous amount of loss in that line. Does that make sense? So what they do is they run 12,000 volt lines or higher. Outside your house, it's probably 3,000 volts. But they're running it countryside higher than, but they're in the 12,000 volt range. But real low current. They can still get the same amount of power out to the residential or commercial sites. So remember, maximum power transfer does not mean maximum voltage efficiency. There's a time when you need maximum power transfer, and there's a time when you need maximum efficiency. When you're designing stereo amplifiers, you're looking for maximum power transfer. When you're trying to deliver power commercially or residential customers, you're looking for maximum voltage efficiency, keeping the currents low. Here's example number 1. I mean, we're done with this lecture. We're going to take a quick look at this example 1 right here for maximum power transfer. But the last lecture, which will be after this one here, for this chapter 5, we're going to work a number of problems that should help you with your homework. For the circuit shown below, determine the value of RL here for maximum power transfer to RL, then determine the amount of power. Similar like those learning assessment problems we had. So you know, whenever you ask for maximum power transfer to a load, you're going to have to Theveninize this circuit here. You have to find a Thevenin equivalent for that circuit. So the path to your solution should be first find an R Thevenin, then find an E Thevenin, and then going back to page 112 and using that equation right here. These are the answers to this problem. Well, keep in mind all the problems that I've shown you to date that we worked here for Thevenin and Norton's theorem and maximum power transfer all had independent sources in them. They all had independent sources. And you know you have to treat dependent sources differently. It's not harder. It just requires double the work. But if you are systematic in your approach, I don't think you're going to have any problem with them. So we'll work some problems in this final lecture coming up. That concludes this lecture.